Yoni. Okay, the next talk is Resultant-based incremental recovery of camera pose from pairwise matches by Yoni, Kasten, Meirav, Galun, and Ronen Basri from Weizmann, and Yoni will be presenting. Thanks.
Thank you for the introduction. So I'm going to talk about my work together with Meirav, Galun, and Ronen Basri from Weizmann Institute about resultant-based incremental recovery of camera pose from pairwise matches. So a sequential structure for motion has been studied deeply in the last few years. Basically, this method takes a collection of images and creates a rich structure of the scene together with camera's locations and orientations. Here you can see an example for the result of the method built in Rome in a day. Here, 2,000 images are registered together to create a rich structure of the Colosseum in Rome. This is a public collection of images, and here you can see each triangle represented one camera of a different photographer. So we will first review their methods, and then we will go to our setup. So basically, this method usually starts with two images, and then point correspondences are searched between these two images. Then, using the 5-point algorithm, the essential matrix is computed between the two cameras. First, usually, the first image is said to have identity rotation and zero translation, and using the essential matrix, the rotation of the second camera is extracted, and the translation of the second camera, which is defined up to scale, is created and is said to be an arbitrary translation with arbitrary scale. Okay. So now where we have two cameras, points can be triangulated from the two views. Each 2D correspondence represents two rays in 3D coordinate system coming from the camera's center, and the intersection of the rays are 3D points in the 3D coordinate system. Now, usually, there are much more point correspondences between the images, and the results will look like the following. Now, given a new camera, we would like to find its position and orientation in the 3D coordinate system relative to the reconstructed scene. So we first find 2D, 3D correspondences from the new image to the 3D scene. And then, given the 2D, 3D correspondences, the new camera is resectioned to the scene such that the 3D points are projected to the 2D observation. This results in the new camera and its rotation and translation parameters. Now that we have three cameras, more points can be triangulated to the scene. Now, more images and more cameras can be inserted to the scene to create a much more richer 3D reconstruction. Each time a camera is added, they use only 2D, 3D correspondences. Now, if we go back to the problem of resection a new camera to the scene, so here, camera 1 and camera 2 has no known rotations and translation, and the rotation and translation of camera 3 is unknown. Now, in order to use 2D, 3D correspondence, the point must be seen from at least two known images, otherwise there is no 3D representation for this point. For example, here you can see 2D correspondence, but there is no 3D information about this point because it is occluded and cannot be seen from image 2. Here is another example. Here there is also only 2D correspondence and no 3D information because this point is occluded from camera 1. So this defines our setup. We would like to be able to find the rotation and translation of a new camera without 3D information at all, only using 2D correspondences from known cameras. Now, several works presented a solution for this problem, And it has been shown that structure for motion using only 2D correspondences, which has much more available information, gets more cameras in the reconstruction. And we will show later that it can also improve the camera's accuracy. However, solving such a polynomial system which resulted for this problem is not easy mission, and hence, previous methods were either inaccurate or slow. So in this work, we present a new formulation for the problem, and using this formulation, we prove a tight bound for the number of solutions of the problem. Lastly, we present an efficient and accurate Dixon resultant solver for the problem, as we will see next. So first, we'll start with our new formulation. So suppose that we have a point correspondence between two images where for one image the rotation and translation is known, and for the other image the rotation and translation is unknown. As a result, the epipolar constraint between the 2 points must be held. However, we assume that the essential matrix E is unknown here. The essential matrix can be expressed by the rotations and translations of the 2 cameras. Now, we can assign the known parameters and get this following equation where the only unknown here are R and T, and P, S, and B are resulted for the input to the problem. Now, we can represent the rotation instead of rotation matrix using quaternion, where quaternion have 4 entries with 1 entry for scalar part and 3 entries for vector part. Now, vec takes only the vector part of the quaternion, and each vector can be extended to be a quaternion by putting 0 in its scalar part. Now, in this equation, the only unknown are again Q and T, which represents the rotation and the translation of the unknown camera. Now, this equation can also be written as follows, where again Q and T are the unknown. Now, this equation is homogeneous in Q, and as a result, the scale of the quaternion can be set arbitrary, and we set it such that the first entry will be 1. And our unknowns are 3 entries of Q and 3 entries of T, and in total, 6 unknowns for the 6 degrees of freedom of this new camera. Now, by using 6 correspondences of our formulation, we get 6 equations in the 6 unknowns, where the unknowns here are Q and T, the rotation and translation of the camera of the central image. So we will see later how we solve these equations, but first let's look a little bit more on our formulation. Here we marked by yellow a cubic term where there is a multiplication of 3 unknowns, and by pink we marked quadratic term where there is a multiplication of 2 unknowns. Then we use the BKK bound, which is a method to bound the number of complex solutions of a polynomial system. And in our case, there is a bound of 160 solutions. However, it was observed previously that this problem has usually 64 solutions. So we would like to see if we can find a tighter bound on the number of complex solutions for the problem using our formulation. First, we know that the cubic term can be represented using quaternion Hamilton product instead of the cross product. Next, we define D to be equal the Hamilton product of T and Q, and then we can express our equations using D and Q and get 2 quadratic terms expressed in D and Q. Now, we have 6 equations of this form, and we can solve for D and Q. Then, given D and Q, T can be extracted uniquely by the following formula. However, we should verify that the scalar term of the quaternion T remains 0. So as a result, we get our 7 constraints, and in total, we have 7 equations in 7 unknowns, 4 entries of D and 3 entries of Q. The BKK bound of this formulation is 64 solutions, and this is compatible with the observations of the previous method of 64 solutions. And we note that the BKK bound of previous work formulation was only 80 solutions. So this is our theoretical part. We first showed a tight bound for the number of complex solutions of the problem. Now we show how we solve these equations. So we have 7 polynomial equations in 7 unknowns. We use the Dixon resultant method, which extract, using the original equations, a set of equations such that it can be expressed as a multiplication of a matrix M times vector V. It does it in a way such that one of the unknowns, in our case Q2, is isolated inside the Dixon matrix, and the rest of the unknowns are in the vector V. The idea is that we can first solve for the isolated unknown, which is called hidden variable, and then we can solve for the rest of the unknowns. So, since the vector V is assumed to be non-zero, the matrix must be singular. And as a result, the determinant of M must be 0. So, it must hold for the right solution of Q2. So Q2 can be found as the solution that zeroes the determinant of M. However, for some formulations, M is always singular, even if Q2 is a solution for the problem, or even if it's not. But in our formulation, it turns out that M is singular only with the right solution for Q2. So we can solve Q2 by solving the determinant of M of Q2 equals 0. And after opening this term, we can see that this is a polynomial equation with one unknown which has 64 complex solutions. So this is actually compatible with our theoretical BKK bound. Now, given solution for 2Q, the rest of the unknowns can be extracted from the null space of M. So more details of Dixon resultant solver and how this matrix is created can be found in our paper. So some implementation details. Extracting the Dixon matrix is a heavy symbolic operation which takes, in the generic implementation, 17 seconds per case, which is too much. However, we designed a specific implementation which we implemented in C, which takes only 6 milliseconds per case. For solving the determinant of M equals 0, we use the generalized eigenvalues method implemented in MATLAB, which takes 14 milliseconds. And more details about our implementation can also be found in the paper. So we compared our method to the previous methods by using synthetic experiments and solving the camera parameters from 2D points. And now, as you can see, our method is much more accurate than the methods of Larson et al. And Stevenius et al., and still more accurate than the method of Pirot et al. However, our method is slower than the method of Larson et al. And Stevenius et al., but is much faster than the method of Pirot et al. Here you can see the distributions of angle error in a logarithmic scale. And as you can see, our method, marked in purple, gets the best result relative to previous methods. The 4+2 case is a case where 4 correspondences come from one camera. This case was only solved first at 2015 by Zeng et al. And our method can also solve this case, and we compared our method to Zeng et al. Method. And again, we can see that our method is more accurate, but a little bit slower. Anyway, both cases can solved in real time by our method and gets very accurate results. For a real-time application, we created robot navigation using landmark experiment. In this setup, two cameras are stationary with known position and orientation, and a robot is moving in the scene with unknown position and orientation. Now each camera sees 4 different landmarks, and our robot can navigate by finding 2D correspondences using the landmarks, and the correspondences are to the known cameras, so we can solve the parameters of the camera of the robot. So here you can see a visualization of the 3D scene. On the right you can see the robot view, and on the left you can see the navigation results. So by green we mark the ground truth position and orientation, and by red we mark the results of Larson et al., and our results marked in blue. So as you can see, in some cases Larson et al.'s method gets good performance, but in some cases they get a very high error. In some cases their error is so big. For here for example the error is more than 3 meters in position error, and by angle they have error of more than 30 degrees. Our method always gets accurate results for this problem. And in the table, you can see it by looking at the median value. Their method performs relatively okay. However, if you look at the mean error, our method is much more accurate than these methods. We also implemented structure for motion pipeline using only 2D correspondences for different data sets. Here you can see visualization of our results. In our pipeline, we also started from 2 cameras and then added cameras one by one using only 2D correspondences, which we solved by our method. We compared our method to Visual SFM, which is a standard sequential structure for motion pipeline, and we see in the table that our method gets better performance than Visual SFM, where Visual SFM uses 2D 3D correspondences to register new cameras to the scene. So to conclude, we have introduced a novel formulation for camera pose estimation from 2D correspondences. We provided a proof showing that there are at most 64 roots for the polynomial system. We constructed a Dixon resultant, which we implemented efficiently by symbolic derivations. And we showed in experiments that our method obtains more accurate solutions than existing methods, and we also showed the utility of the method in sequential structure for motion pipeline. Thank you very much.
Thanks, Yoni. Questions? Okay, so let's thank Yoni again.